The next thing I want to talk about are the zeros of polynomial functions. So if f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. Now, these values are also the roots or solutions of the polynomial equation. And actually, all real roots are x-intercepts on the graph of the polynomial function. Now, a little interesting thing here is that the degree will tell you up to how many roots you can have. This is a little kind of tip. I'm not sure if your book focuses on that at all, but it's really a nice tip. So in our first example we're going to do, we have a degree of 3, so we can have up to 3 solutions here. You actually do have exactly 3 solutions if you're willing to include imaginary numbers as well as repeat solutions. So sometimes if you get a repeat solution that occurs more than once, you would have exactly 3 in the mix. So let's go ahead and try this. So what we're going to do is we're going to set our function equal to 0, and we're going to go ahead and solve. Now, for polynomials, we don't really have a lot of solving techniques at this point. The main one that we have is factoring. So that's probably going to be your go-to for a lot of this, is to see if you can factor. I'm noticing that I have 4 terms here, so I'm going to go ahead and factor this using grouping method. So what I'm going to do is I'm going to group my first 2 terms and my last 2 terms together. I don't want to change the sign, so the x is negative and the 3 is negative, but I just put a plus sign in the middle. Putting a plus sign doesn't change any signs. It just lets me to kind of put my 2 groups a little bit, make them more clear to see. And then what I do is I take the GCF out of each group. So in the first group, I have x squared in common, and then I'm left with x plus 3. And in the second group, they both have a factor of -1. So when I factor that out, I also have x plus 3. When you're factoring by grouping, you should have a repeat factor here. So the last step is now to write that repeat factor only one time, and then you write what's left over. So it's going to be x squared, and this is the same thing as -1. Now, see if you can factor again. I do notice here that I have an x squared piece left, and this is actually the difference of 2 squares, and I can factor as x plus 1, x minus 1. Don't forget to, if you need help with factoring, I have a lot of videos available it's in the MAT162 class on my YouTube channel. So if you go in there, there's a ton of videos on factoring, and I do cover factoring by grouping there as well, including things like difference of squares, etc. So if you need that extra help, go in and check out some of those videos. Once we're done here, what we can do is we can set each factor equal to 0 and solve. So here we're subtracting 3. Here you're subtracting 1, and here you would add 1. And I can see I have 3 solutions there. So the zeros are -3, -1, and 1. When we write the zeros, we usually just write the numbers. They usually, if they ask for zeros, they probably just want the answer. They don't necessarily want the full point or anything like that. Because they are all real, they are also x-intercepts on the graph. So if you actually have real solutions here, you're going to see x-intercepts on your graph. And graphing is actually a nice way to check. So I'm going to bring that up for us so we can check this one. All right, just give me 1 minute to find my Desmos screen here. There we go. All right, so I'm going to go ahead and type in our polynomial function. And if you look here, you can notice that you see three x-intercepts. I have one here at -3, one here at -1, and one here at 1. So using the graph is a really, really nice tool to check your work algebraically, or even the other way around. If you have to find the zeros, you can use the graph also as a starting point to at least find the real zeros. Sometimes you do have zeros that are not real, right? So you could have imaginary answers too. Imaginary answers will not appear as x-intercepts, right? Because we're only graphing the real numbers. So you have to be a little careful, but if you have real zeros, you should see those as x-intercepts. All right, let's do another one. All right, so for the zeros, I'm going to set the entire function equal to 0. All right, and I'm going to look and see if I have a GCF here that I can factor out. And let's see, what I have is, I'm noticing that they all have at least an x squared term. And I personally don't really like having a negative to start. So I'm actually going to factor out a negative x squared term. So this gives me positive x squared minus 4x and then plus 4. So if I had 4 here and I take out 2, I have 2 left. Here I had 3 and I took out 2, so I have 1 left. Here they both got taken out. And then just be careful because I took out a negative, my signs are switching as well. And then now you may notice that we can actually factor this. Let's see, 2 and 2. And now I'm going to set each factor equal to 0 and solve. So I have negative x squared equal to 0, x minus 2 equals 0, x minus 2 equals 0. Here we can get rid of that negative, divide it by -1 on both sides, and you still have x squared equals 0. Normally, when you take a square root, you would take plus or minus the square root of both sides and get 2 answers, but 0 is just 0. So technically, you do have that 2 answer idea. Don't forget when you have squares, so be careful there. But because it's just 0, we end up with only 1 answer. And then here, when you solve, you end up again with a repeat answer. So our unique answers are x equals 0 and x equals 2. Notice though that my degree was 4, so you could have up to 4 solutions. So 2 solutions are fine. And I did tell you that you have actually exactly 4 solutions if you're willing to include repeat answers and imaginary numbers. So here, I actually have 4 solutions, 1, 2, and then 3, 4. It just happens that I have the value of 2 twice and the value of 0 twice. So you do have that idea of having 4 solutions there. It's just that you have repeats. So I only actually have 2 unique answers in this case. So the zeros are 0 and 2. And like I mentioned before, you will notice that you have x-intercepts here of 0, 0, and also 2, 0. Remember, in your x-intercept, your y value is 0. So that's how we can find our points. I won't graph this one, but I encourage you to pause the video and try it at home and make sure you can see that the graph actually does have 2 x-intercepts, one at 0 and one at 2. All right, so some more work with zeros. We can use the results of factoring to express a polynomial as a product of factors. So for example, in the previous example, we were able to factor. We took that negative, I did it this way. I took the negative x squared out at the same time. Notice here that because you have x minus 2 written twice, that's actually a square. So we're just writing it here as a square term instead, but it's the same factorization that we had. So we're noticing that the x minus 2 occurs twice. In factoring, if the same factor, x minus a number, occurs a certain amount of times, we call that 0 a 0 with multiplicity k, whatever that value is. So in this case, both 0 and 2 have multiplicity of 2, right? If I look in the above example, this one has a 2 and this one has a 2. And as we saw, both of those solutions appear twice. the value of 2 appeared twice, and the value of 0 appeared twice. So we say that it has multiplicity of 2, meaning that that answer appears twice. If it had multiplicity of 3, it would be that same answer appearing 3 times, and so on. Multiplicities do have a connection with the graph as well. So if your 0 has an even multiplicity, so 2, 4, 6, etc., what happens is the graph touches the x-axis, but doesn't go through it, and it turns around, it kind of bounces back. If you have odd multiplicity, so 1, 3, 5, 7, etc., the graph actually goes right through the x-axis. We do also see that the graph tends to flatten out when you have zeros of higher multiplicity. So if you have multiplicity greater than 1, you will actually see that your graph is a little bit flatter in those areas. All right, so let's try an example, and then we can also check with the graph too. So here we're already pre-factored. So we want to find the zeros of our polynomial and then give the multiplicity of each 0 and then state if it crosses or touches the axis. So for your zeros here, remember that when we're solving to find zeros, we're setting each factor equal to 0, right? I don't need to do the 1/2, it's not going to affect anything, but I would set x plus 1 equals to 0 and 2x minus 3 equals 0. And when I solve, I have my first 0 is -1. And then my other 0 is 3/2. Now for the first one, notice that the factor of x plus 1 only occurs one time. If there's no exponent there, there is a 1. So the 0, -1, has multiplicity 1, but this factor appears twice. So it has multiplicity 2. Okay. Now, I don't care about the 1/2. If there was a variable there, if there was an x, that's different. Then I would have another solution. I'd have a solution of x equals 0. So I'd have to deal with the multiplicity there as well. But only if you have variables. I don't care about just numbers. The other thing we have to figure out is if it's going to cross or actually just touch the axis. So if you go back to the page before, when your multiplicity is even, what happens is the graph touches the axis and kind of bounces back up or back down. It doesn't actually go through the axis. When the multiplicity is odd, that's when it goes through. So for this case, this one has odd multiplicity. So this is going to actually cross the x-axis. This second one has even multiplicity, so it's going to just touch the axis and turn around. So let's go ahead and look at this graph also. Okay, so here's our graph. Notice that we had 2 zeros. We had 1 0 at -1, which is right here, and the other 0 was at 3/2, which is 1.5. Because they're both real numbers, we're going to see them as x-intercepts. So zeros that are real are always going to be your x-intercepts. So I can see that on the graph. The other thing we noticed is that the 0 of -1 here had multiplicity of 1. It was odd. When you have odd multiplicity, you're going to go right through that x-axis. So see how it goes right through the axis? Our other 0 had even multiplicity. It was 2. And when you have even multiplicity, you don't go through the axis. You touch it and then you bounce back up or you turn around. So notice here that we touch the axis, but it goes right back up. It doesn't actually go through the axis. So from that equation, we can actually figure out quite a lot of what's going on. Not just with the end behavior we already saw, but actually at the zeros. So we can see if it's going through or if it's bouncing back up. This one's a little hard to see here, but the higher the multiplicity, the flatter this gets. So for instance, let's say I change this to multiplicity of 4. See how it gets a lot flatter? Or if I change it to multiplicity of 6, it gets even flatter. So the higher the multiplicity, the flatter you get at that point. And the same thing here too. So let's say I change this to it, I'll keep it odd, but maybe 3. See how it got a little flatter at the axis, even though it still went through. Or if I make it 5, it gets even more flat at the axis. It's never going to be horizontal, but it's going to be flatter. So you'll notice that as well with higher multiplicities. All right. The next thing I want to talk about here is the intermediate value theorem. We often abbreviate it as IVT, so I'm just going to do that in the lecture notes to save us some writing. It's actually a really, really important theorem. It's one that I'm going to just talk about quickly, but it's actually really important. So it says that if f is a polynomial function with real coefficients, so again, we're not talking imaginary numbers here, and let's say that f of a and f of b have opposite signs. Now remember, these are your y values. Then what happens is there's at least one value of c between a and b where f of c is 0. Now, what does all this mean? It means that you have at least one real root between a and b. Let me show you an example. I think it'll make a little bit more sense. So we're going to show that the polynomial function has a real 0 between 2 and 3. And this means x equals 2 and x equals 3. So I'm going to plug those values in. When I plug in f of 2, I get 2 cubed minus 2 times 2 minus 5. So I get 8 minus 4 minus 5, which is -1. When I plug in 3, I have 3 cubed, which is 27. 2 times 3 is 6. So I have 27 minus 6 minus 5. So what's that? It's going to give me 16. Now I'm not drawing the full graph here. I'm not doing n values or anything like that. But let's see what's going on here. So at 2, so when x equals 2, we're at, let's see, -1. So at 2, you're at -1. And then when you're at 3, you're up at 16. So 1, 2, 3, 4, 5, 6, 7, 8, all the way up at 16. So your point is like maybe somewhere up here. So what we're saying is that somewhere between 2 and 3, then you must cross through that x-axis. There's no way to go from here to here without going through the x-axis. That's what the intermediate value theorem is saying, is that if you have one y output that's negative and one that's positive, then in between there must be at least one root. There could be more than one. Maybe it passes through a bunch of times or something. I don't know. But if you have a y value that's negative and a y value that's positive, then you must cross that x-axis at some point between those 2 points, which means that you have a root, you have a solution. And a lot of times this is a starting point, particularly with really tough equations and applications. It may be very difficult to solve polynomial equations. So sometimes the intermediate value theorem is a place that we start first. We kind of narrow down where the solution could be. And if we know that we have a negative and a positive y value, we know that we have a solution somewhere in there. And it's worth like working harder to find that answer. Polynomials are very, very difficult to solve in the real world. They don't often factor, so it's a lot harder. So this theorem tells us that yes, there is a solution somewhere in between there. Okay. All right. And then we do, just as a side note, we do have technology that can help us find these values. So you can always guess and check, right? You could try plugging in like 2.1, 2.9 and kind of find that solution. But we do have technology. So there is a 0 function on like the TI 8384 series that can help you find that exact value if you need it. Or if you're on Desmos, right, you can usually zoom in and find that approximate value there. A lot of times our answers end up being irrational. So some sort of non-terminating repeating decimal. But like I said, they can be difficult to find because they're not usually factorable. But that theorem lets us know that we do have a solution somewhere in there. So we can use a graph or a technology tool to help us find that solution. All right, one more set of definitions here. So the next idea is a turning point. So here you have the graph of x to the fifth minus 6x cubed plus 8x plus 1. It has 4 smooth turning points. At each turning point, the graph changes direction from increasing to decreasing or vice versa. That's kind of why it's called a turning point, right? It turns direction, either going from up to down or from down to up. What you want to notice too is that if a polynomial function has degree n, then the graph has at most n minus 1 turning points. So here our graph is degree 5. So n minus 1 would be 5 minus 1 equals 4. So you can have at most 4 turning points. Now, another way to think of a turning point is that it is either a relative max or a relative minimum. And this is a really kind of nice idea here because we already know about maxes and mins. So a turning point is just another word for a max or a min. It's that place where the graph changes from increasing to decreasing or from decreasing to increasing and vice versa. So notice this graph has 1, 2, 3, 4 turning points. So it has 2 relative maxes, 2 relative mins, so 4 altogether. Now, without the aid of a graphing utility, so technology or knowledge of calculus, it's actually very difficult or sometimes impossible to locate the exact turning points of polynomial functions with degrees greater than 2. So what you can do again is you can test values, like I said, just kind of plug in values getting closer and closer to where you think it is, or you can use a graph or something like that, or technology. But polynomial functions in the real world can be quite difficult to work with. So we do actually rely on technology a lot of times for help with that. At least Desmos is pretty nice, where you can go to Desmos and you know, they usually do tell you that those approximate points that you need on the graph. So that's a really nice graphing utility to check out.